In this video, Team 20 will demonstrate Ronaldo, a robot capable of playing soccer. We were tasked with designing, building, and testing a soccer robot that adhered to the locally modified RoboCup small size league laws outlined in the F180 Small League Laws document. This project provided key learning opportunities to develop technical and project management skills. Not only this, but the project, much like the actual RoboCup challenge, sparks interest and pushes robotic innovation in areas that have extraordinary commercial applications. Our main goal was to design a soccer robot that could kick as many goals as possible in 5 minutes. Ideally, the system as a whole should be able to consistently and reliably kick goals at a rate of 2 goals per minute. To do this, the robot must be able to detect an orange golf ball, navigate towards it, and one of 2 goals, whilst avoiding obstacles within a 2x2 metre playing field. A reliable drive system is fundamental to the success of any mobile robot. To compete against his opponents, Ronaldo needed a drive system that could consistently achieve a translational velocity of 0.5 meters per second whilst maintaining a heading angle. It was decided that Ronaldo should have a differential drive system, as it was the simplest and most time-effective way to meet these requirements and get Ronaldo on the move. The system consisted of 2 wheels at the front and a caster wheel at the back. The 2 wheels are driven by 2 50-to-1 ratio geared motors that give Ronaldo a top speed of 0.5 meters per second. These motors are controlled by a Teensy 3.2 through a dual motor driver. Ronaldo changes direction by receiving a string from the AI navigation to the Teensy with inputs that change the relative PWM signal sent to each wheel.
One of the most important aspects of a robotic system is how it interprets its environment. A soccer player needs to be able to see. Ronaldo uses a wide field of view camera to interpret his environment. The feed from his camera is processed through image analysis to separate the ball, the obstacles or other players, and the goals, and mathematical methods are used to determine the range and bearing of the elements in real time, the same way a real player's brain would analyze the image from their eyes. Researchers at QUT have used similar robotic vision techniques before, such as in Harvey the capsicum harvester. The data, the ranges and bearings from the processed image, is then sent to the artificial intelligence system, Ronaldo's decision-making complex.
The AI and navigation system is the most important subsystem of a soccer-playing robot. For Ronaldo to be able to competently play a game of soccer, he must have a robust central nervous system, aka subsystem communications. He must be able to search for the ball, seek the ball, search for the goals, seek the goals, and score goals, all while avoiding obstacles. For Ronaldo to get to the ball, he had the following state machine. This allowed him to proficiently change between states. The range and bearing to the obstacles was passed to the AI navigation subsystem through specifically written functions. Once Ronaldo decided where he wanted to move, a command string was sent over USB serial, aka his central nervous system, to a Teensy 3.2 which controlled his motors and where he'd move. Ronaldo would move to the ball by aligning himself for the ball, then translating directly to it. If an obstacle was in his way, he would move to avoid it through using his repulsive field. The vision, the AI, and the navigation subsystems were all run on Ronaldo's main brain, a Raspberry Pi 3. Motor control was undertaken by his Teensy 3.2. The Raspberry Pi 3 operated in Python 3.5, and the Teensy 3.2 operated in C. This allowed clear and concise communication between all subsystems, which allowed Ronaldo to play the game he lives for.
With all of his subsystems together, Ronaldo was able to detect multiple obstacles, the ball, and the goals. The AI system used this information to communicate with the drive system to avoid obstacles and move towards the ball rapidly. With minor improvements, Ronaldo will be able to use his vision of the goals to move the ball towards them and score. At their heart, sports are objective-based games, which can involve many different elements: dexterity, problem-solving, and spatial awareness, to name a few. These elements have significant applications in mechatronics, both in robotic sports and wider functions. Developing Ronaldo has taught Team 20 many new things about mechatronics and how robotic sports can further the cutting edge of mechatronic systems.